Hello, everyone. I hope everyone is doing well. My name is Yao, and today I'll be talking about subglacial evolving hydraulic transmissivity beneath the Greenland subglacial lakes. So, thousands of subglacial lakes forms annually on the surface of the Greenland ice sheet in response to seasonal surface melt. And you can see that many of these lakes drain rapidly, transporting water through vertical hydrofractures directly to the bottom of the ice sheet. So this is the observation of North Lake that drains through a fracture and is almost entirely emptied within a few hours. The same observation of lake drainage can be found in different years and occurs around the same time of the year in June and July. Observations show that after a lake drains, the ice sheet is uplifted and water is transiently stored beneath the ice sheet, forming a water-filled blister. But over a few days, this uplift goes down, and this could be caused by water leaking from the blister into the surrounding subglacial drainage system. This water flow at the ice bed interface is important because it modifies the boundary condition of the ice sheet. This water lubrication at the interface between ice sheet and bedrock can reduce the friction and change the speed of ice flow. For example, this is an observational evidence that water lubrication at the bed after the injection of meltwater directly impact the sliding velocity of the ice. Despite the importance of ice bed lubrication, the drainage system efficiency under 1 kilometer of ice is very difficult to measure and remains a source of uncertainty in flow simulations. So here we develop a new method to use this surface observation of the uplift relaxation as a natural experiment to probe the drainage system efficiency. And here's a data set provided by my colleague, Laura Stevens. Here she used a dense network of GPS uplift data to estimate the distribution of the blister height after the injection of water. Here the red color denote positive vertical uplift and blue is negative. Let's see the video again. So as you can see, after the injection, the blister height decreased in a time scale of a few days. So here we look at three different lakes and collect the data of blister height that peaks and then relax as a function of time for 5 different lake drainage events. Interestingly, we observed that relaxation timescale ranges from as short as 12 hours to as long as 10 days. And our goal here is to understand what governs the relaxation dynamics and then why the relaxation time varies dramatically between different relaxation events. So before jumping into the model, I want to point out that at the locations where the lakes form, roughly 1 kilometer above sea levels, previous models by Dow et al. Indicate that after a lake drainage event, short discontinuous channels can form, but these channels do not significantly affect the subglacial water pressure or discharge. Therefore, we assume that the channels are small enough that the flow in a subglacial system under the lakes can be modeled as a continuous sheet that obeys Darcy's law. So for a subglacial sheet that the drainage efficiency can be described by the hydraulic transmissivity, here denoted by K times H naught. Darcy's law has been used for several types of distributed systems, such as films, linked cavities, and canals. The key feature shared by this distributed system is that the water flux in the water sheet is increased linearly with the hydraulic potential gradient. And next, to understand the blister relaxation process over the drainage system, we develop a simple model. So the injection of water into the ice bed interface has been previously modeled as a fluid-driven fracture in a semi-infinite elastic medium. And after the injection, the elastic relaxation of ice drives the thinning of the fluid-filled fracture along the ice bed interface. However, the interface between ice and bedrock is covered with subglacial water networks. Therefore, here we consider the coupling between a permeable sheet and a fluid-driven fracture, where the water in a fracture is allowed to permeate through a distributed water sheet. And a similar system has been studied previously by Huey et al., considering the bending region where the thickness of the ice sheet is much smaller compared to the radius of the blister. But here we focus on the region for a semi-infinite crack, which is appropriate because the blister radius is roughly the same, is on the same order as the ice sheet thickness. So here is a fluid filled blister beneath the elastic medium. The red arrows denote the water flow directions. Around the blister, there are elastic stresses caused by this vertical elastic deformation, which force the blister to relax. And along the water flow, there's viscous resistance in the flow, both in the blister and in the porous sheet. We also estimate that the hydrostatic pressure is small compared to the typical elastic stresses. So therefore, the relaxation is driven by this elastic deformation, but resisted by the viscous resistance in the water flow. So after some algebra, we obtain an ODE for blister volume. Here, the volume of the blister and the time is non-dimensionalized. The first term represents the viscous stresses in the porous layer. The second term is the viscous stresses in the blister. And the third term represents the driving force of the system, the elastic stresses. Here, this A parameter represents the ratio between the viscous resistance in the blister compared with the viscous resistance in the porous substrate. And in the field observations, we estimate that this A parameter is much smaller than 1, meaning that the viscous stresses in the blister is negligibly small. In this case, the numerical solution for blister volume as a function of time approach a analytical exponential behavior, which is shown by this red dashed line. So our model predicts that the relaxation dynamics is close to a exponential decay. Now let's look at the time scale that we use to rescale time. We can understand this relaxation time scale through simple scaling argument by balancing the elastic stresses with the viscous pressure in the porous layer and considering the volume conservation law. We find that the relaxation time is inversely proportional to the sheet transmissivity and also depends on the radius of the blister. Note that the transmissivity is the permeability of the sheet times the thickness. So to check whether the relaxation timescale makes sense, we really need to test the model with a controllable system where we know the permeability of the porous sheet. And here I show a lab experiment performed by Danielle Chase, who is currently a PhD student at Princeton. In her experiment, a thick elastic PDMS layer is adhered to a porous substrate with a known permeability. And the viscous fluid is injected and peels the interface between the elastic sheet and the porous substrate to form a fluid-filled blister. So you can see after the fluid injection, the radius of the blister remains roughly constant. Let's see the video again. Yeah, the radius is roughly constant. And we see that the elastic relaxation drives the fluid in the blister to permeate through the porous substrate. So the benefit of the experiment is that we can control the permeability of the porous substrate. Here I plot the measured blister volume as a function of time for 3 different permeabilities. We found that the exponential solutions agreed well with the experiment, with all the 3 experiments with only 1 fitting parameter. And also after rescaling the data with a characteristic time and characteristic volume, the data for 3 different permeabilities collapse onto a universal curve, demonstrating the success of our scaling in capturing the relationship between relaxation time and permeability. So now we will use this model to understand field observations. First, we see that our exponential solution, shown by this black dashed line, fits well to the blister height relaxation data. Second, we see that the wide range of relaxation time can be explained by different estimates of transmissivity. What this shows is that ice sheet relax faster on the ice bed interface with higher transmissivity. And when we look at the time of lake drainage, we also find that transmissivity is much larger later in the melt season than early in the melt season. and we will address this in a few slides. So next, we put all this data set on the same plot. And again, this is the blister height that relaxes over time. And after we rescale the blister height with initial height and the time with the relaxation time scale, we show that the curves collapse onto a universal shape and can be described by our exponential solution. Therefore, despite the variability of the local lake basing and the relaxation time span, this collapse of the data onto a single curve indicates that the universality of uplift relaxation between the lakes, which can be explained by our simple model. And this exponential model serves as a new tool to determine the basal transmissivity on the lakes using only surface uplift data. So now we can estimate the transmissivity of the water flow at the ice bed interface. We can look at the evolution of transmissivity over time. Theoretically, it has been shown by Schuf that during the melt season, the ice bed interface switches from a less efficient water network to a more efficient channelized drainage system. This color scale denotes the cross-sectional area of the water network that was more or less uniform in the beginning, but then localized into channels over time. So this evolution has been demonstrated by tracer experiment where the water flow speed is measured by tracking the travel time of a tracer between a given input and output. And Chandler et al. Found that over the course of the melt season, the water velocity increased over time, which suggests the formation of channels. And their result implies that efficient system developed up to 41 kilometers from the margin. However, at elevations higher than 1 kilometer above sea levels, close to where the lakes form, such as this moorland here, the velocity is averaged along a 41-kilometer long trajectory. Therefore, it is unclear how much drainage characteristics evolve locally at the high elevation regions near the lakes. So here we use our new method to monitor the evolution of transmissivity locally under the surface lakes. These lakes formed at ice thickness around 1 kilometer or thicker, therefore allow us to probe transmissivity further inland under ice thicker than 1 kilometer thick. So from these 5 drainage events, the basal transmissivity estimated locally under the lake can increase by up to 2 orders of magnitude over the course of the melt season. The blister relaxes slower in the early melt season when the supraglacial drainage system is less efficient, but relax faster later in the melt season, indicating a more efficient drainage system with higher transmissivity. Our results suggest that the transmissivity can evolve locally at the lake elevations around 1 kilometer above sea level. So in comparison, the tracer experiment showed that the supraglacial efficiency average along the tracer pathway increased over time, and our method showed that the transmissivity can evolve locally under the lakes. And currently, no observations of transmissivity exist for elevations above the 5 lakes investigated in our study. These observations are needed to understand the evolving subglacial hydrology and its impact on the sliding in ice sheet interior. All right, so this is a summary and look forward to seeing you virtually in AGU.